learned in the last class. So among these tool wear, tool life and machinability, we discussed the tool wear first, and we have understood the consequences of tool wear. So if tool wears out, what is the problem? Can anybody list out one or two issues if there is tool wear? What are the problems with tool wear?
Sir, it might damage the machine which we are using.
Machine. Okay, it may be true, but it is not direct effect. Machine will not be affected by the tool wear. In general, it is very minute effect will be there, not to the machine. Okay, we cannot say it is completely not there, but almost negligible. Tool wear effect on the machine is negligible. It is mainly on the workpiece. Okay. If the tool wears out, you will not get the proper surface finish on the component that you are machining, and you will not get the proper dimensions during cutting. So your intention is to cut, let us say, okay, 5 mm depth, but because the tool has worn out, now you will cut only 4.5 mm because your total depth of cut has reduced effectively. Your intention is to go 5 mm deep, but because 0.5 mm is already removed from the tool, you will go up to 4.5. So there is a change in dimension, change in surface roughness. Because initially there was a very sharp tool tip. Now there is some curvature on the tool. So obviously it will affect the surface finish. And of course, tool life will come down because some amount has gone from the tool. Now it is weak, its strength has reduced, and there will be some vibrations and chatter. So they may lead to the failure of the machine, but its effect is very, very less. We cannot say directly that because of tool wear, machine life has come down. Okay. So like that, there are some adverse effects of tool wear. Now, how does this tool fail? Okay, what are the different modes of tool failure? At least one or two. There are in fact three. Okay. Three modes of tool failure. I'm asking about tool failure, not exactly tool wear.
Thermal cracking and softening.
Okay, fine. Thermal cracking. Okay, that is not actually the whatever you said is correct, but we have given three categories. Like one is mechanical breakage. So that means the tool is breaking out because of its brittleness or high force, etc. And another is plastic deformation. So tool is losing its shape because of high temperature. And third one is due to wear, tool wear. Okay, gradual tool wear. That is blunting of tool. So to reduce all these three, so mechanical breakage, it is due to lack of strength or toughness. Okay. So if toughness is high, then the mechanical breakage will not be there. Similarly, thermal deformation. So if you want to arrest it, so your tool should have good hot hardness. Of course, wear, you should have good wear resistance to reduce the wear. So these are the three modes of tool failure and the reasons, okay, and how you may overcome those kind of failures. And of course, the reasons, this thermal cracking and softening, whatever you have told, that comes under plastic deformation category. Okay. So this is because of high temperature. Gradual wear, of course, due to abrasion, and of course adhesion, etc. There are many reasons. And mechanical chipping, okay, will lead to the breakage of the cutting tool. And of course, what is the preferred mode of tool failure?
Gradual wear, sir.
Yes. So gradual wear of the cutting tool, that is what we prefer. Now, what are the locations of tool wear? Are the types of tool wear, I will say. And a single point turning tool, where will you find the wear, or what are the types of wear?
Crater wear and flank wear.
Yes. So crater wear, flank wear. Crater wear, what is the location of the crater wear?
Rake surface. I mean rake face.
Yes, yes. Flank wear, so of course it is directly given in, it is on the flank surface. So mainly on the principal flank, and minor portion will be there on the auxiliary flank as well. And we have seen the pictures, etc. And crater wear appears like a crater or a tiny, what I would say, shallow, okay, this concave shape, shallow concave shape can be seen on the rake surface, that is crater wear. On the flank surface, at the cutting edge, okay, some portion of the material will be removed from the tool, okay, up to certain depth or certain depth means I am talking about vertically. So that is called flank wear. Now, of course, towards the end of this flank wear, you will have one notch. Okay. So that is due to abrasive action and the slip, not slip, the passing of the chip. Okay. So the edge of the chip will be cutting this tool over a period of time. Because chip surface may be hard sometimes because of oxidation also, and of course some foreign particles may also be there. And we have seen pictorial and we have seen some terminology also related to wear, how we will represent wear, KT, etc. And we have also seen the ISO standards for tool wear. So you can remember these. Okay, the average flank wear is 0.3 mm. That is one criteria. Maximum flank wear is 0.6 mm. That is another. Coming to crater wear, it is 0.06 mm plus 0.3 times of feed. That is the limit for crater wear. Okay, that is KT. Of course, catastrophic failure is anyhow there. And coming to the mechanisms of wear, okay, tool is wearing out over a period of time, and what are the reasons for it? So mainly there are four: adhesion, abrasion, diffusion, and fatigue. Mainly these four. Adhesion, just chip is sticking to the tool, then it is taking away some material. Abrasion, some hard particle is rubbing against the tool surface. So what are those hard particles? Maybe some foreign particles in the material that you are measuring. Diffusion where, okay, some of the chemical elements like ferrous or chromium, manganese, they will flow from tool to the workpiece or the workpiece to the tool. So tool is getting softened, and okay, so due to that, some material is lost from the tool to the workpiece. Okay, migration of the material due to density difference. And fatigue wear, so over a period, so if there is some loading coming onto the surface of the tool, so over a period it will just wear out. Okay, fatigue. We have seen that pictorially how this wear takes place, etc. And we have also seen the effect of temperature on wear. So with temperature, the tool wear increases up to some limit. Okay, gradually it will increase with temperature, but after some limit, there will be sudden, okay, or a rapid increase in the crater wear with temperature. And we have seen the curve relation between the cutting time and the tool wear. So initial stages there will be rapid tool wear due to mechanical chipping, etc. And for some long time you will have gradual wear. So towards the end there will be rapid wear. We have discussed this with some analogy with pencil, sharp pencil. So up to that we have seen in the previous lecture. Now let us continue. So many times it is important to memorize what has happened in the previous class, so that you will once again we are repeating the key points. Now the next step is, once you understand what is where and how it is happening, what is the mechanism, etc. Now how do you measure? We have understood that if where, let us say 0.03 is the flank wear. So then we are saying tool is failed. Now how do you determine that 0.03? Okay, there are different methods. One way is quantitatively you are measuring the wear. That is one method. Other way is qualitatively you will say that tool has worn out. Okay, there are different methods for identifying these. So direct method. So under this optical method by microscope. So there will be you will take out the tool. Okay, whenever you feel that tool has worn out, how do you feel? You will understand that more power is being used. Okay, you can see the power requirement. Okay, directly using a dynamometer, you will get the forces. Force will be converted to power, or otherwise more force is required. So that means something has happened with the tool. Or you are getting poor surface finish. You will understand that tool has worn out. So there will be some indications. Or there is some different sound is coming out. So based on that, you will understand that tool might have worn out. You will take out and you will measure the tool wear using some microscope. It is called tool maker's microscope. So using that, now you will measure the height of the flank wear. Okay, what is the width of the flank wear? What is the depth of the what is the width of the crater wear? What is the depth of the crater wear, etc. You will measure. If it is within the limits, so then a tool is okay. There may be other factors that are contributing to this abnormal behavior in the machining process. If the measured wear is beyond the limits, then you have to replace the tool or you have to regrind the tool and use it. Okay. So you are directly measuring here, okay, with the help of this tool maker's microscope. That is direct method. Now indirect method, this is qualitative, okay, or you can estimate also, but it is indirect. Directly you are not measuring the wear. So you are looking at the force component. So machine is taking some amount of force, okay, cutting force. Some cutting force is there. There are three components of the force. So you look at them. Okay, if they are not varying much, cutting force is almost constant. Okay, there is no problem. Suddenly there is increase in cutting force. Okay, then you can understand that tool has worn out. Okay, that is how you measure using dynamometer. Dynamometer is used to measure the force. And power also. Okay, dynamometer will give you the force. Okay, force into velocity is this power. Okay, so from that also you can say whether the tool has worn out. Now temperature. So during machining, okay, we are getting some kind of temperature. It will fluctuate obviously, but if it is within the range, okay. So suddenly there is a high increase in temperature. So then you can understand that tool has worn out. Okay. Now surface finish is another thing. Suddenly you are getting poor surface finish on the machined component. Then also you can understand that tool has worn out. Vibration. So there is okay, tool is now suddenly vibrating. Some sound will also come if it is vibrating. Okay. So based on that, you can say that tool has worn out. Acoustic emission. So this is by sound. Okay. So suddenly there will be some abnormal sound coming from the machining zone. Okay. Or from the machine. So that can be measured. Yeah. Okay. Sound intensity can be measured. So based on that, you can understand that whether tool has worn or not or not. So these are the methods of measuring the tool wear, directly or indirectly. Now next is this tool life. So you can just read out this. So length of cutting time that a tool can be used before the flank wear reaches the limiting width of the flank wear. So this is one definition. So here if you carefully observe, we are talking about only flank wear here. Okay. And the width of the flank wear. What is the general width? We have seen as per ISO 0.03 mm. Okay, average width. So if a tool reaches 0.03 mm, okay, width for the flank wear, average width. So then you will say tool life is over. Okay, if it is beyond 0.03, you will say tool, okay, life is completed. So why we are talking about only flank wear? Why not crater wear? Okay, or why not notch wear, etc. Because flank wear takes place quickly compared to crater wear. Okay. So generally, if the tool is failing due to wear, it is mainly due to flank wear only. That's why directly definition is given like that. Crater wear takes very gradually compared to flank wear. Abrasive action is faster compared to this adhesion. Okay. Through adhesion, very minor amount will be lost. Through abrasion, okay, it will be considerably high. So before tool reaches that width on the flank surface, okay, whatever amount of time you have used the tool, so that is called as the tool life. Now, this is one famous equation for estimating the tool life. Very simple equation. V T power small n is equal to C. Now what is V? What is V?
Cutting velocity.
Yes. So V is cutting velocity. Now T is tool life. And N and C are constants. Okay, they were experimentally determined for various tool materials and workpiece combinations, and data book is available. Okay. So here you can understand from this equation, tool life depends on what? Tool life is dependent on which parameter?
Velocity.
Cutting velocity. So there is no other parameter, only cutting velocity. As for this, okay, as per this Taylor's equation. So tool life mainly depends on cutting velocity. That is the point you can understand. So V, that is cutting speed, generally given in meter per minute, okay, or meter per second also. Then you can convert. Then T is the tool life in minutes. C is Taylor's tool life constant. Okay, so that is in meter per minute. Understand? Now N is Taylor's exponent. So okay, these are experimentally determined, C and N. Now these N values are like this for various tool materials. N is equal to 0.1 to 0.2 for HSS tool. Okay. And similarly 0.2 to 0.49 for carbide, 0.621 for ceramic tools. Okay. So these are taken from the data books, but these values are determined experimentally. And for different other materials, plain carbon steel, N and C values are given. So these N and C values, if you see at the bottom of the table, they are also dependent on feed and depth of cut. If feed rate is 0.25, depth of cut is 2.5. So under that condition, these are the N and C values for various tool materials. If feed and depth of cut varies, then okay, the N and C values will also vary. And you can also understand, just observe, feed is 0.25 mm per revolution, depth of cut 2.5. Generally, feed is less and depth of cut is more. That too, more or less, it is 5 times relation. Okay, it is not always true, but generally 5 times of feed value will give you the value of depth of cut, okay, for a good machining process. But we can choose our feed and depth of cut, we can vary. So that is one observation just on this table. And plain carbon steel, these are the values. Okay, steel cutting. When you are cutting steel using this plain carbon steel, if you are cutting non-steel, so what is the value? Similarly, HSS, steel, non-steel. Because steels are very widely used materials, so steel is given. And if you are cutting non-steel, other than steel, because steel contains carbon also, many of these tool materials will also contain carbon. So that's why steels are specially given. Cement tools for steel, cemented carbides for steels, ceramic for steels, etc. Now, there is some extended tool life equation. Okay, so tool life is not only dependent on V, cutting velocity. It also depends on feed and depth of cut. So that is the modified or extended Taylor's tool life equation given by other researchers. Okay. So it is like this: Vt power n, f power n1, d power n2 is equal to some constant. Now other tool life equation. So apart from speed, feed, depth of cut, this tool life is also dependent on hardness. BHM is Brinell's hardness number. I think somebody has unmuted. They can mute. And please, all of you, unmute yourself. Sorry, mute. And V, of course, we all know this. V is cutting speed, T is tool life, D depth of cut, N1, N2, 3, all are exponents. K is a constant. Now all these have to be experimentally determined. From the experimental data, you have to find out N, N1, N2, N3, etc. Okay, their ranges are given. Now, effect of rake angle and clearance angle on tool life. Now, with the increase in rake angle, what is happening to tool life? So, all of you mute yourself, please. Somebody has unmuted and left it. Okay. Now, rake angle. So, rake angle generally varies from -5 to 10. This is the general range. Okay. On a single point turning tool. Or if it is a positive rake angle, generally it will be somewhere around 6 degree, 8 degree, okay, 5 to 8 degree in that range. We'll get the good tool life actually here. Now, if you see, if the rake angle is negative, that too beyond -5, so that means tool is not sharp, okay, cutting edge is not sharp, something like that.
Hello.
Yeah, who is speaking? You can identify the person and inform that the person who is creating. Okay, now it is fine. Okay. So tool is, if there is a negative tool angle, okay, cutting edge is not sharp, but tool strength is high. Okay. So in that case, you will have good tool life. But having good tool life, not good tool life, here what will happen is the cutting process is taking place and you are not getting the desired surface finish. Okay. Immediately you are losing the required surface finish. So that's why tool life is less, because it is not sharp. Tool is not sharp when the rake angle is negative, or if it is negative rake angle, that too high negative rake angle, tool edge is not sharp. Okay. So it will easily, with a small amount of material coming out, you will get the poor surface, etc. So that's why at a very high negative rake angles, so tool is giving very less life. So somewhere around -5 to 10, it is giving good tool life, particularly around some 5 to 6 degrees positive rake angle, you are getting good tool life. So why you are getting good tool life? Because tool is sharp here. Okay. So if the tool is sharp, it can easily cut the material. You are not accepting too much force. So then wear will be less. If you are okay, exerting more force, then obviously where will be more rubbing action is there. So if you are applying less force, obviously tool will last a little bit longer. But if it is becoming too high, rake angle is becoming too high, tool is becoming thin. Okay, it is becoming very thin, and there can be mechanical breakage of the tool tip. Understand? So due to that, the tool life will decrease. Okay. So at a very high negative rake angle, okay, or very low rake angle directly. So your tool life is less because you are accepting high force and removing the material. And the intermediate stage, because tool is sharp, okay, there is enough strength for the cutting tool. So tool life is good. So beyond, okay, some 10 degree, so tool is becoming too thin and tool life is decreasing. That is the effect of rake angle. Now coming to the clearance angle, if it is too low, okay, then obviously there will be more rubbing action between the flank surface and the workpiece material. So tool life will be less. So after some time, maybe around 2 to 6 degree range, okay, there is enough clearance between the tool and the machined surface. But anyhow, some amount of contact is unavoidable. So, but wear is gradual, so tool life is more in this range. Again, if it is becoming too high clearance angle, then again tool will become thin from the flank side, this side. Okay, it is like this for one tool, let us say. For another tool, let us say. So it is too much clearance angle, then it is okay, its strength is less, so it may break, okay, very easily. So that's why. So if it is too high, also tool wear will be more. So you will try to have this optimum range for this rake angle and clearance angle in general. Okay. For special cases, of course, so there will be exemptions. Like if you are cutting very hard material, very high strength material, then you may have to go for negative rake angle. But of course, in that case also, generally will not go beyond -5, etc. Okay. Unless it is absolutely necessary. Now, so far we have seen what is tool wear, okay, what is the tool life, and what is the effect of tool geometry, that is rake angle and clearance angle and tool wear, etc. Now let us see what is machinability. Okay, we'll say some material, okay, its machinability is good. For some material, machinability is not good. Now, how do you say it quantitatively? Okay, qualitatively, you can say some, let us say mild steel has good machinability. And some other material, if you say some inconel, nickel based super alloy, its machinability is less. So qualitatively we are saying, but quantitatively, how do you define? So first of all, let us try to understand what is machinability. So it is generally applied to the machining properties of work material. Machinability is a property of the workpiece material, that's it. And it refers to material, that is work response to machining. So how a material is responding to the machining process. If you are trying to cut that on a lathe machine or a milling machine, so how the workpiece is behaving. Now it is the ability of the work material to be machined. Okay, you can also say machinability as this. These are different versions for defining this machinability. Machinability indicates how easily and fast a material can be machined. Now, how do you quantify that? Okay, qualitative definitions we have seen here. how do you quantify this machinability? So machinability can be measured or quantified mostly in terms of, first is tool life. Now, tool life which substantially influences productivity and economy in machining. So let us say if you are machining one particular workpiece, let us say mild steel, for example. So if the tool life is more, is high during the machining of that mild steel material, then you will say that mild steel material has good machinability. So if the tool life is more, when you are machining a particular material, so you will say that particular material has good machinability. Now another thing is magnitude of the cutting forces. So during cutting process, so with less power consumption only, if you are able to cut the material, then you will say that particular material has good machinability characteristics. Now surface finish. So if you are getting good surface finish during machining process, under the same cutting parameters, let us say if you are cutting a titanium alloy and you are cutting a mild steel under the same machining conditions using the same cutting tool. So let us say you are getting very good surface finish for one material, titanium and mild steel you are considering. Let us say mild steel, with mild steel you are getting good surface finish. So then also you can say that mild steel has good machinability characteristics. So finally, you can define machinability as this. Machinability rating, in short, MR, is defined as this. Speed of machining the work, giving 60-minute tool life. Understand? And divided by speed of machining standard material, giving 60-minute tool life into 100. Understand? Now speed of machining the work, giving 60-minute tool life. What does it mean? Now let us say we are considering some mild steel. So during the machining of mild steel, as per Taylor's equation, it is Vt power m equal to C. Okay. Now you are fixing T. If it is 60 minutes and you know the n and C values, you put those values. Now what is the velocity? So for mild steel, you have taken the velocity. Similarly, you will take a standard material. Now what is this standard material? Generally on steel material. So for steel, now what is the velocity when the tool life is 60 and the N and C values are same? So you have one velocity here, one velocity here, you divide them and multiply with 100. Then you will get the machinability rating. So you can see here a standard material, maybe one kind of steel, some number is there. Now specimen that you are cutting, it may be mild steel or it may be aluminum or it may be magnesium alloy, nickel alloy, titanium alloy, whatever it may be. So you got at different speeds, you have for different tool lives rather, for 60-minute tool life, what is the corresponding velocity? So here it is 60, it is 100. So 60 by 100 into 100. Okay, you are getting 60 as machinability rating in that particular case. So now you can define machinability again. Okay, we have seen what is the meaning of machinability. It is the ease of machining a particular material. Okay. Now, if you want to define machinability, so this is a simple definition: ability of being machined. Okay. And you can also define this as ease of machining. This is very simple definition of machinability. Okay. Machining ability is machinability, that's it. The ability of being machined. So how do you quantify using MR, machinability rating? Now, ease of machining or machinability characteristics of any tool work page, okay, a particular tool and workpiece combination is judged by cutting forces. So you are considering a mild steel, okay, and HSS tool. So this combination is important. So if you are machining mild steel with HSS, you may get good tool life. Okay, if you are machining mild steel with some carbide insert, let us say, you may not be getting good tool life, for example. So this combination also plays a role. Tool wear, okay, machinability depends on the tool wear also. Tool wear varies between the material to material. Mild steel, tungsten carbide combination, okay, tool wear rate is different. Mild steel and HSS tool wear rate is different. Understand? So machinability is defined between these two. It is not absolutely the only workpiece characteristic. It is the combined effect. Okay. When you are machining mild steel with HSS, then you can say what is the machinability. If you are machining mild steel with tungsten carbide, what is machinability? If you are machining mild steel with some other material, okay, high carbon steel, what is machinability? Combination is important. Tool wear, tool life. Okay, if your cutting force is high, okay, poor machinability. Tool wear is high, poor machinability. Tool life is high, good machinability. Surface finish is good machinability. Cutting temperature is high, poor machinability. Based on chip forms, okay, if the chip is a continuous chip and there is no built-up edge, then machinability is good. So you can see cutting forces less means good machinability. Tool wear less, good machinability. Tool life, long tool life, good machinability. Surface finish is good machinability. Cutting temperature is less, then you will say good machinability. Uniform, okay, chips, then you will say good machinability. So these are the indications for the machinability. So influencing parameters on machinability. So properties of workpiece material itself is important. Whether workpiece is very hard or ductile, brittle. So based on that, okay, or does it have good wear properties, or depending upon the properties of workpiece material, machinability varies. Now property cutting tool. So cutting tool material and cutting tool geometry both will affect the machinability. So if the cutting tool is sharp and machinability may be good. If the cutting tool is blunt, machinability may not be good. But we cannot use always very sharp tools for all the materials. Depending upon the workpiece also, you have to select. Now levels of the process parameters. So if you are keeping high depth of cut, a high feed and high speed for machining, let us say in Corel, so it may not work. At low speed, at high speed and low depth of cut, low feed, machinability may be good. So it is dependent on process parameters also. Machining environment, whether you are using cutting fluid, if you are using cutting fluid, machinability may be good. If you are not using custom, machinability may not be good. Strength, rigidity, and stability of the machine will also affect the machinability. If the tool is firmly held in the tool post, then machinability will be good. Otherwise, if the tool is moving or vibrating, good cutting will not take place, so machinability will become poor. Kind of machining operations done in given machine tool. So what is the operation you are carrying out? That will also define the machinability. Whether you are going for plane turning, or are you doing some facing operation, step turning, or some forming operation, some shape you are cutting, based on that. Also, machinability varies. Pretty simple plane turning machinability may be good, but if you are trying for some grooving operation using same HSS tool, grooving tool, so you are using, and HSS single point turning tool you are using. So with the same workpiece material, but there can be variation in machinability. Now, how do you improve the machinability? Chemical composition. Okay. So by varying the chemical composition of the cutting tool, that means you are putting some foreign material like some chromium, vanadium, manganese, etc., cobalt in the cutting tool, so that some hardness, corrosion resistance, wear resistance, etc., will increase for the cutting tool. So then you will get the good machinability. Understand? So that is by varying the chemical composition. Microstructure. Microstructure of both workpiece and tool, will impact the machinability. So if the very fine microstructure is there for the cutting tool, then obviously its wear will be less. Okay, and vice versa. So microstructure will also affect the machinability. Fine microstructure for either workpiece or tool will give you good machinability. Treatment given to the metal, whether you have done some heat treatment operation or you have increased the toughness of the material, or tool material, or whether you have softened the workpiece material. So, whatever treatment you do, so that will also improve the machinability. So let us stop here. We'll see few numerical problems in the next class related to Taylor tool life equation. So the numericals related to Taylor's tool life equation are very, very important. In terms of gate, etc. IES, whatever exam, public sector exam or any interview, Taylor tool life equation problems are very, very important and very easy also, because we are dealing with simple equation Vt power n equal to C, like that. So just like merchant theory, this is also very important, but relatively easy compared to merchant theory. We will see them in the next class. So that's all for today. Anything to discuss?
No, sir.
Yeah. So I hope everything is fine. We shall see our meeting tomorrow. See. Okay. Thank you. Have a good day.
Thank you, sir.